The first thing we're going to try to understand is linear density. So what that means is so density is kind of how much mass there is per amount of volume. So, Swiss cheese with lots of holes in it is not as dense as Swiss cheese without lots of holes. And so the formula here from physics says the mass is equal to the volume, the amount of space it takes up, times the density. And the mass is a measure of kind of how much stuff there is. And then it says for a one-dimensional object, so we're thinking like a coil of rope, or a rope or a wire, something like that, then the linear density, that's the amount of density, just because it's one-dimensional, we call it linear, times the length gives you the mass. And so if we want to, for example, say you have this piece of wire here, it has a linear density of 3, and it has a length of 5, then it could have a mass of 3 times 5, or 15. Now that was really basic and without even worrying about units, but that's kind of the idea. Now, where the calculus comes in is what if the density varies? What if the density right here for this at this point on the rod is not the same as the density over here at this point? How can we find the total mass if we don't know, if the density is changing? And what we're going to do is we're going to do calculus. We're going to take this rod and we're going to slice it up into itty-bitty little thin slices. And in every slice, if this is the slice here at the point xi, and it's right here, we're going to take this little chunk out. It's going to have a width of delta x. And on that little chunk, we can assume that the density is constant. So we can plug in our x value into our linear density function. And if we take our x value there, which would be x, 4 minus x, and we multiply by our delta x, the width of our little slice, then this is giving us our density times our length. And what does that give us? That gives us mass. But that's only mass for one little slice. If we want the mass for the whole thing, we're going to have to add them up. And the easiest way to add up a bunch of infinitely thin little slices is to integrate. So we're going to integrate our density function, and then our delta x turns into a dx when it gets infinitely small, from 0, if that's where we want to start here, that we call that x equals 0, up to wherever the rod ends. And that's going to give us our mass. So so this is what we just said, right? Rho there stands for density. So we've got our density, we're going to integrate it, and it's going to give us our mass. So if we do this example we've got here, how would we actually do that? Well, if we wanted the actual mass, we would have to FOIL this out. Then we'll do our power rules. Then we'll take our answer and we'll plug in using the fundamental theorem of calculus. So we'll have 2 4 squared minus 4 cubed over 3. That's plugging in 4. Minus, well, when we plug in 0, we're just going to get 0. And that's our mass. That's linear density. Here's another example. It says find the mass of a thin wire with the following linear density function. And so this one's a little bit funny because our wire here, it's 3 units long. 1, 2, 3. But for the first two, the density function is 2x plus 1. And for the last part here, the density function is x squared plus 1. So we're going to deal with this the same way we deal with piecewise functions normally, or physically we can think of it as almost as cutting this wire and finding the mass of each piece and then adding them together. So our total mass here is going to be the integral from 0 to 2 of 2x plus 1 plus the integral from 2 to 3 of x squared plus 1. All right, the next application we're going to talk about is work. So this is a physics concept. Work is the amount of, I guess, work required to move an object. So what that is you're going to take how much force you have to use to move that object and multiply it by the distance that you move that object. And that's the total amount of work that you spent. All right, and so force is defined as mass times acceleration. And then we just talked about mass being volume times density. If it's a 3D thing. If it was a 2D thing, it would be area times density. The single dimensional things, the lines we just did, were length times density. All right, so if we want to find the total work, we're going to end up probably doing something like volume times density to give us mass times acceleration to give us force times distance to give us work. And we're going to end up doing all those things together if we want to find work. A couple of things to know about work is that the U.S. measurement system and the metric system are a little bit different here, because for the U.S. we have a measurement for force, it's pounds, distance is feet, and then work is measured in foot-pounds. So that is number of feet times number of pounds. In the metric system, they don't have a unit that's for force, they have a unit for mass, that's kilograms, and then you have to multiply it by the acceleration to get the meters. This is usually what they give you, is the kilograms and the meters. There is a force here, newtons, but usually they don't give you a problem statement in newtons. Then you have to make sure your distance is given to you in meters as well, and the total, the work here, is in joules. And so whenever you're doing a problem, before you start, make sure all your forces are in pounds, all your distances are in feet. So if they give it to you in inches, convert to feet. And that'll give you the work in foot-pounds for the U.S. system. Or if you're in the metric system, make sure your mass is in kilograms, your acceleration is in meters, and then everything, and your distance is in meters, and then everything else will work out. So an example of work, it says find the work required to lift a 25-pound barbell off the floor and place it on a bench 30 inches high. So the 25 pounds, that's our force. And the 30 inches, that's our distance, except remember the distance has to be in feet, so 30 inches is 2.5 feet. And the way you find that is to say 30 divided by 12, because there's 30 inches and 12 inches in 1 foot. So now, how much work is it? The work is going to be the force, 25, times the distance, 2.5, to give you 62.5 foot-pounds as your work. Now, here the calculus comes in again when you have something that's not consistent. So it could be that the force is changing, it could be that the distance is changing, or it could be both. So the first example here we're going to have is going to be the force changing. So if the force is changing, then we're going to do almost exactly what we just did with density. We're going to take our force and we're going to take whatever our thing is, we're going to chop it up in little bits, and we're just going to go a distance of dx every time. And then we'll add up all of those forces to get, or all of those little bits of work to get our total work. So we're going to have a little bit of work being your force at a particular point x, let's call it xi bar, times the distance of that little tiny section x, and that gives you your little tiny bit of work. And then if you integrate this expression, that adds up all the work. So here's an example of that. Hooke's law is a law for string. It says the force required to maintain a string stretched x units beyond its natural length in either direction is f of x, that's your force, equals kx. where K is the spring constant. So depending on your spring, you're going to have a different value of K. You guys have played with springs before, right? Some of them are stretchier, some of them are harder to stretch. That stretchiness measure, that's where K comes in. So there's our spring, and if we put X right there, that's the equilibrium. What that means is that that's where the spring would be if you just set it on a table and you left it alone. And so the work required to keep it there, the force you need, is 0. But as soon as you try to stretch that string, it takes positive force. And as soon as you try to compress that string, it takes force in the negative direction in order to do that. And so when we're trying to find out the work you're doing while stretching it or compressing it, that amount of force changes. It's easy to stretch it when it's close to resting. It's pretty easy to stretch it or compress it. But when you get out farther away, it suddenly gets really difficult to stretch it anymore, or really difficult to compress it even more. This is a lifting problem. So lifting problems, this is where distance is going to vary. Because if you're lifting, for example, here you're lifting this cable up to the roof, then, this little slice right here that they gave you, you have to lift it up this distance. But if you took a little slice up here near the top, you barely need to lift that at all, so that takes a lot less work. And if you take a little slice down here at the bottom, you got to lift that the whole way. So that takes more work. So if you're doing something like lifting up a cable, we are going to have distance vary. All right, so how are we going to do this? We're going to chop it up into little segments like this. And on each little segment, right there, we're going to be able to assume that for that little piece, the distance is the same. All right, so remember, work is force times distance. All right, so if we say X maybe is the distance from the top, so let's call this X is the distance from the top. Then our distance will be X. And then we need to find the force. Now the whole cable is 400 pounds though. So if we're trying to find the little bit of work done on that little distance delta X, the distance you're going to have to lift it up is going to be X, let's say that. And then how much is that little bit going to weigh? Well, 400 pounds of cable is 100 feet long. That means that this cable is 4 pounds per foot. And that would tell us that if we only have a little tiny delta X amount, then it would be 4 times delta X pounds would be how much our little tiny bit there would weigh. So delta W, the little bit of work, would be X, that's the distance, times 4 delta X. That's how much the little tiny bit, the number of pounds, that little tiny bit of chain weighs. Alright, so now there's our equation for a little bit of force. Now we want to add up all those forces, so what do? We integrate. So we're going to integrate 4x, and then remember the delta x turns into a dx. And then where do we start? Well, we start up here at the top where x is 0, and we stop when we've gotten the whole chain. So that's down here when x is 100. And that'll give us the total work of picking up that chain. Our tank shaped like this is actually formed by revolving this parabola around the y-axis. And it has a height of 10 meters. So that means from here to here, it's 10. And it's filled with water. And the curve here that we're rotating around is y equals 5x squared. That's what we're spinning around. And it says, how much work does it take to pump the water out of the top of the tank? So if you look at this example, this is something where both distance and force are going to vary. And distance is going to vary because at each slice here, if we slice up our water, each one of these slices has to go a different distance to get out of the top of the container. If I go back here to our book, we can actually look at a figure of this. There we are. So there's our parabolic container. We're cutting it up into slices. The more slices, thinner it is, right? The closer it is to being exact. And then, depending on where your slice is, this slice is down here at the bottom, right? So it's got a long way to go to get all the way out to the top. In this example, they actually are lifting it up to above the surface of the container. I think our problem, we're only lifting it right to the surface. And then we're going to imagine there's some kind of hose or something to take it away. But if we were to look instead at one of these higher up slices, you know, that one, that's it. That's as far as it has to go to get out of the container. It hardly had to go at all.
It's also important that where you take the slices are where the water is. It doesn't matter the shape of the container. You start at the bottom of the water and you stop at the top of the water.
So whenever we're lifting stuff up like this, we always slice it horizontally so that
all the water in the same slice will have the same distance to travel to get to the top.
Usually when you do these, if they give you y equals 5x squared as your function, they're telling you already what your variables stand for. They're telling you that this way is x, with this being 0, and that this way is y, with this being 0 right here. So the distance you're going to have to take, if this is your typical slice here, the one that's blue, and it's at, the slice is at y, just like when you're doing shells, your slice is at y. To get from that slice up out of the top, we need to go this distance, right? That's the distance we want to find. This distance from the axis up to our slice, that's y. And the total distance is 10. So the distance our slice has to move is 10 minus y. So once again, that little green area, that's y. I've just made it red. And then this is what we want to find right here. And we know that the total is 10. So if we take the 10, we take away the y, we get the distance we need to go. That's 10 minus y. Now the other thing we have to worry about is force. In this case, force, we are going to want to think of this as mass times acceleration. And the acceleration is going to be the acceleration due to gravity. And we're going to have to think of mass as volume times density. So lots of physics words going around here, but if you can just kind of remember these formulas, how they go together, then you can figure out which pieces you need for your particular problem. So we need to find volume, density, and acceleration. Now the good news is that they give you the density right there, it's 1,000. And acceleration due to gravity is always the same, it's 9.8. And so now we just need volume. So we need to find the volume of one of these little slices. And the volume there is going to be the area of that little slice times the thickness. And the thickness is delta y. And the area, that's a circle, right? This is a disk, right? This is like the disk method. So the area of that circle is pi radius squared. And the radius is determined by the function. So right there, that red distance there, that's the radius of our disk. And so that's our function. Our function is y equals 5x squared. But since it's horizontal, we need to solve this for x. So x is going to be square root of y over 5. Alright, so that's the amount of, that's the little bit of force it's going to take. So that means our little bit of work for that one slice is going to be pi square root of y over 5 squared delta y, that's our volume, times 1,000, that's our density, times 9.8, that's the acceleration due to gravity. All that together gives you the force, times 10 minus y, that's the distance it has to go. And then to add up all of those little pieces of work, we integrate. And so we get pi. I'm going to put all these constants together. 1,000 times 9.8, that's 9800. In fact, and usually we write the pi afterwards, right? So we'll say 9800 pi. And then we have 10 minus y. Square root of y over 5 squared is just y over 5. And then the delta y becomes dy. And so there's our work. And where do we integrate from? Well, y starts at 0. That's where we're going to start slicing. We're going to slice all the way up to the top, which is 10. So we're going to integrate from 0 to 10. And now this was this looks like it's very complicated. But remember that when you go to integrate, you can just pull those constants out front. So this integral actually isn't really much more complicated than a lot of them you've worked on before. In fact, you can even pull that 5 out front. And there you are. So to solve it, you have 9800 pi over 5 times the integral from 0 to 10 of 10y minus y squared dy, which is, using the power rule here, 5y squared minus y cubed over 3 from 0 to 10, which is, when I plug in, got to remember that these constants get distributed to all of it, so I need some big parentheses. 5 times 10 squared minus 10 cubed over 3 minus, when I plug in 0, I'm going to get 0. So there we are. That's our work. The very last kind we're going to talk about is pressure. So pressure, in particular, we mean hydrostatic pressure. And that means pressure of water, still water. So, the pressure of water on the side of a swimming pool. The book explains, it says if you're in a pool and you're standing on the bottom and you can feel the pressure of all that water right above your head, that's hydrostatic pressure. If you're in the wall here, the wall also feels that pressure. And if you can imagine, the pressure is heavier down here than it is up here. So if you're building a pool, you better make sure it's very strong down there at the bottom. Another example of where this happens a lot is a dam. So if you have a dam, and here's your river behind it, here's your lake at the bottom, all that water is leaning against that dam, and so that's a lot of hydrostatic pressure. Okay, so here we can see that we know force is mass times acceleration, and mass is volume times density times gravity. So our total force here is the area times the height times rho, that's your density, times gravity. Because our volume we're getting by a slice times its height. And then the pressure part is defined to be the force divided by the area. So if we divide by area, we're left with just the density, the gravity, and the height. So let's look at a problem that would be like this. Okay, so here again, the force is the area of the strip. So there is, okay, so then the total force we're looking for is the area of the strip times the pressure. And so pressure is what we just talked about on the last page. Density, that's going to be a constant. Gravity, that's going to be a constant. And then this is the distance, the height. This is how far it is under the water. So if this is the top here of your dam, then it's at the that's the number A. This is your y value. That's the number y. That distance between them, just like in the previous problem, that distance is a minus y. And so that's what they're saying here. And then the area of this little strip of water, that area is all at the same pressure because it's all at the same depth. So we can use all of it together. So we need to find the length of the strip. And so this W of y, that's supposed to be that length, or they're using W, I think, for width. The width of this strip times the delta y. The delta y is how thick the strip is. And if you put all those together, that's going to give you your force. So here, let's try a problem. Oh, this is the same thing we just said again, only they're saying, you can add up all those little strips, it turns into the integral. Okay, so we have a large vertical dam in the shape of a symmetric trapezoid that has a height of 30 meters, a width of 20 meters at the base, and a width of 40 meters at the top. And what is the total force on the face of the dam when the reservoir is full? So using this formula they give us, it's going to be the integral. Right, so let's put a y is going to be our up and down here. So this way is y. So here's a slice. This distance is going to be y. So y is going to start at 0, and it's going to go up to 30. Right there. Okay, so now we need our density, that's rho. And we'll use from the previous problem, water has a density of 1,000. We need our gravity. That's 9.8 when we're in the metric system. We need our depth. So that is the total depth, 30, minus y. And then the last thing we need here, this is depth. The last thing we need is the width of each rectangle. And then we're going to have dy. That's the height of each rectangle. And so these two together give you the area. Okay, so how do we find that width? That's the hard part. So we go back to our picture here. We want to find this length right here. And all we know about it is that this distance is y. We also know that we could draw a bigger triangle here, like this, and we know things about that bigger triangle. It had this one side, the long side is 30, and this side over here, we can find that, right? Because we can split the top up. This is 20. The total is 40, so this must be 10, and this must be 10. Because it says it's symmetric. It means it's the same on both sides. So we have a big triangle that's 10 by 30. And so our little triangle inside here, this is a similar triangle. You guys remember doing this from related rates? This similar triangle is going to be the thing we want to know by y. So the thing we want to know divided by y is just like 10 divided by 30. So the little piece here that we want to know is 1/3 y. Now if we look here, this middle is going to be 20, and the other side, because it's symmetric, is a question mark again. So the total width is 20, that's the middle part, plus 2 question marks. So it's 20 plus 2 times 1/3 y. And that's what we're going to put in here for the width. 20 plus 2/3 y. And we found that just by looking at the geometry of the shapes that they gave us. And that's all the pieces together. And then you would just, if you wanted to integrate, you would pull out these constants, and you would FOIL together these two terms. And it would actually be very straightforward to integrate. And that's it. That's a bunch of different ways that we can use integrals in physical situations. These are the kinds of situations you're going to be responsible for. So make sure you understand each one of these, what the formula is. I would also recommend reading this section because they did a really good job giving lots of details and explaining the physics behind each of these. And it'll help you kind of understand what you're doing. The main idea here is that in each of these situations, we have something that we need to be constant, and we can only treat it as constant on a thin little slice. So we slice it up into thin little slices, figure out what we're trying to find on that slice, and then use integration to add up all the slices.